In this chapter, we will talk about how to manage a bond portfolio. To manage a bond portfolio, you are to manage the interest rate risk. If you think about the bond pricing formula, the price of the bond is the discount value of all future cash flows. The future cash flows, coupon payments, and fees value are fixed numbers written on the contract. So in the pricing formula, the only variable that can be changed is the discount rate or the interest rate. So when you are managing a bond, the only uncertainty is the discount rate. If the interest rate goes up, the bond will experience capital loss because when the interest goes up, the price will go down. There is an inverse relationship in the price and the discount rate. When the discount rate or the interest rate goes down, the bondholder will experience capital gains because when the interest rate falls, the price will go up. You will have a capital gain. So the gains or the loss makes the fixed income investment very risky, even if the coupon and principal payments are guaranteed. To measure the interest rate, we are going to calculate the Mercaldi's duration. I'm going to show you the formula, the calculation, and then I will show you the intuition and how to interpret the duration. So who needs to measure the interest rate risk? Basically anyone who purchased the fixed income securities, anyone who purchased the bonds will try to measure the interest rate risk. For example, pension funds, insurance companies, banks, hedge funds, mutual funds. Those are institutional investors investing in large amount of bonds. So they will have a portfolio manager measure the interest risk and try to control the interest rate risk. So for the risk management purpose, managing the interest rate risk, you are trying to reduce the risk associated with interest rate changes. To measure the interest rate risk, we will have to calculate the duration or Mercaldi's duration. It is a measure of how sensitive a bond market price to the interest rate change. So the interest rate here we are talking about is the yield to maturity. The Mercaldi's duration calculation is rather complicated. D, the duration, or Mercaldi's duration, is 1 over P times the discounted cash flow weighted time. So the duration is in the unit of time. So if you want to take a closer look at this formula, duration D is actually the weighted average of time, while the weight here, WT, is the discounted value of the cash flow over the total market price. In this chapter, I will use this very simple numeric example to show you how to calculate the duration. So what is the duration of a 8% semi-annual coupon bond with 2 years to maturity? Annual yield to maturity is 10%. Well, first of all, we need to calculate the price of the bond. To calculate the price of the bond, we're going to use the formula. 8% coupon rate semi-annual payment means each payment in every 6 months is $40, which is 8% times $1,000 face value divided by 2. 2 years means we have 4 6-month period. Face value $1,000. Plug in all the numbers and we get the price is $964. So this is the price. Secondly, we're going to calculate the duration. So the price, $964, 1 over the price is outside right here. And then we are going to calculate the discounted cash flow weighted average of time period. Specifically, for the coupon payments, we are going to have 4 $40 coupon payment. Each will be discounted at 1 plus 5% to the appropriate time period. 5% here is the half of the yield to maturity because we're talking about half years. And then the last discounted cash flow is the face value discounted back, which is $1,000 divided by 1 plus 5% to the power of, here in this particular example, 4 years. So the capital T is 4. Okay, so the capital T is 4 because this is in the fourth time period. When you plug in all these numbers, you calculate the duration, which is 3.77 periods, because we are talking about 6 months. So 3.77 is the semi-annual periods, divided by 2, which is 1.885 years. So the duration of this bond is 1.885 years. So what does 1.885 years mean? It means this 2-year bond takes about 1.885 years to take back your initial investment, $964. The remaining 0.015 years are the time period you are going to collect the interest payment. Let's use a very simple example to illustrate the logic behind the duration. We are going to use a 2-year annual coupon payment bond to illustrate the idea and show you why duration is a discounted cash flow weighted time period. So the unit of the duration is time period. In this example, we have a 2-year bond, 10% coupon paid annually. Current yield to maturity is 8%. Okay? So first of all, let's calculate the D. If you look at the simplified formula, D is the summation of time of weighted average of time, WT times T. So what is WT? Let's take a look. So D equals 1 first time period times the discounted value over the total bond price in the first period. Okay, so let's look at the first term. The first term is 1. 1 is time period in year 1. So 1 times. In the numerator, we have the $10 divided by 1.08. So in the first year, you receive the $10 coupon payment, discounted back to time period 0, which is $10 divided by 1.08. That is the discounted value of the first year's cash flow. In the denominator is the price of the bond. Okay, remember the price of this 2-year bond is going to be the 2 cash flow discounted back to time 0. The first cash flow is the $10 coupon payment divided by 1 plus 8%. The second cash flow payment in this bond is the $100 face value plus $10 coupon. Because you receive $110 in year 2, so it's going to be discounted at 1 plus 8% squared. So the denominator is the price of the bond. The numerator of the ratio is the discounted value of the first year's cash flow. Then we move on to the second term, which is 2 times. So the 2 really means T equals 2 in the second year or the second period, times. Now the ratio, if you look at the top of the ratio, which is $110 divided by 1 plus 8% squared. So $110 is the second year's coupon payment plus the face value $100. So that is the second year's or the terminal year's total cash flows. The cash flow is received in 2 years, so discounted at 1 plus 8% squared, you get the present value of the second year's cash flow divided by the bond price. So basically the ratio measures what is the proportion of the discount value of the second year's cash flow to the total bond price. As you can see, the weight 1, W1, is only 0.0894 because of the bond price. The first coupon payment, $10, is only a very small portion. So the weight you put in the first year is very low, while the weight you put on the second year on the number 2 is very high because the face value payback accounts for a huge portion of the total bond price. So the weight for year 2, W2, is about 0.911. So the weight you put on the second year is very high because in the second year or in the terminal year, you are receiving the face value payback. That is always going to account for a huge portion of the total bond price. When you plug in all the numbers in our calculation, 1 times the weight 1 plus 2 times weight 2, you calculate the duration, which is 1.911 years. Okay, so the intuition here is it takes about 1.911 years to take back your initial investment. Initial investment is the price you paid for the bond, and the remaining 0.089 years are the periods you're collecting interest payment. So the intuition here is the current value of each period's cash flow has different sensitivity to the yield. The value of more distinct cash flow will be more sensitive because the cash flow to be received in the far future will be discounted back at a higher level of t, which is in the power of the discount rate. The sensitivity of the bond overall value will be the average of those different sensitivities. But if you look at the weight, the biggest weight always comes from the final payment, because in the final payment, you are going to receive the face value payment. So the Mercaldi's duration is always going to be closer to the yield to maturity. In this case, it's closer to 2 than to 1, because in the second year, you have the face value payback. If we have a 4-year coupon bond, then the Mercaldi's duration number is going to be very close to 4, because in year 4, you will receive most of the payment. So year 4 will have the highest weight. Let's take a look at the following 4 bonds and see which bond is more sensitive to the change of the interest rate. In this picture, on the vertical line, we have the percentage change in the bond price. On the horizontal line, we have the percentage change in the yield to maturity. So basically what you can read is, for 1% change in the yield to maturity, how many percentage change in the bond price? Okay, so this is how we read this picture. Now we have 4 bonds, A, B, C, and D. Bond A has coupon rate 12%, maturity 5 years. Initial yield to maturity 10%, means initially when the bond is issued, the yield to maturity is 10%. But later on, after the bond is sold, the yield to maturity is the market rates. It will change all the time, which means the price of the bond A will also change all the time because the yield is changing. Coupon rate 12%, maturity 5 years. When you look at bond B, Bond B has the same coupon rate, 12%, but 30 years maturity. Initial yield to maturity is still 10%. Comparing Bond A and B, which one will have more sensitivity to the change of the yield? Means for 1% change in the yield to maturity, which bond will have the biggest change in the bond price? Of course, bond B will be more sensitive to the change in the yield to maturity because the maturity of the bond B 30 years, while bond A 5 years. So when you are discounting the distinct cash flows for bond B, a small change in the yield to maturity will cause a huge change in the bond price. Think about year 30 when you're receiving the face value $1,000 plus the last coupon payment. 1% change of the yield to the power of 30 years. The change is going to be a lot higher than the percentage change of the 5-year maturity because for bond A, the most distinct cash flow is in year 5. When you're calculating the numbers, the face value and the coupon payment will be discounted at 1 plus r to the power of 5. So 1% change in the yield to the power of 5, the impact will be lower than the 30-year bond. When you're comparing bond B and bond C, both bonds have the same maturity 30 years, initial yield to maturity 10%. But bond B has a higher coupon rate, 12%. Bond C has a lower coupon rate, only 3%. Comparing bond B and C, which one is more sensitive to the percentage change in the yield? Well, bond C will be more sensitive because bond C has a lower coupon rate, while bond B has a higher coupon rate. Means the percentage of the last coupon payment plus the face value means the last year's coupon payment plus the face value is going to account a huge portion of the total cash flows for bond C, while bond B has higher coupon payment, means in early years you are getting a bigger portion of the coupon. So the last year's cash flow will account for a relatively small percentage of the total cash flows you receive. So bond C will be more sensitive because your biggest cash payment will be in the last year, and the farther in the timeline, the more sensitive the bond price to the percentage change in the yield. Finally, when you're comparing bond C and bond D, both of them have coupon rate 3%, maturity 30 years, initial yield to maturity, one is 10%, another one is 6%. Okay, so bond C initially the yield is 10%, while bond D is 6%. Which one is more sensitive to the percentage change in the yield? While D is more sensitive comparing to C because initially the yield to maturity is a small number. So for the same 1% change in the yield, the relative size of the change is going to be bigger to bond D than bond C. So finally, if you look at the picture, the more sensitive of the bond price to the percentage change of the yield, the steeper the slope. So bond D has the steepest slope of the curve, while bond A has the lowest sensitivity, so the slope of the curve is the flattest. From the previous picture, we can draw some conclusions on the interest rate sensitivity. Because there is inverse relationship between the price and the yield, The first conclusion we can draw is long-term bonds tend to be more price-sensitive than the short-term bond. Referring to the picture, if you look at bond B and bond A, bond B has longer maturity, so the sensitivity of the bond B is higher than bond C. So the slope of the bond B curve is steeper than the curve of the bond A. The second conclusion is, as maturity increases, price sensitivity increases at a decreasing rate, means it gets flatter. Bond B is 6 times maturity of A, but has less than 6 times sensitivity. The next conclusion is price sensitivity is inversely related to the bond coupon rate. Referring to the bond B versus bond C, bond B has higher coupon than bond C, so the sensitivity of the bond B is lower. The next conclusion is price sensitivity is inversely related to the yield to maturity at which the bond is selling. So when you are comparing C and D, C has a higher yield to maturity, and it is less sensitive to the change in the yield comparing to the bond D. In this, there are 4 rules for duration. The first rule is duration of zero coupon bond is the time to maturity. Because there are no coupon payments, the 100% weight is given to the last year, so the duration equals the time to maturity. For example, 5-year zero coupon bonds duration is 5 years. You can verify this by plugging in all the numbers in our duration formula. The second rule is duration is smaller for bond with larger coupons. Remember in our previous picture comparing bond B and C? So the duration is smaller for bond with larger coupons, means the duration of the bond B will be smaller than the duration of bond C. Rule number 3, duration generally increases with the time to maturity because the last payment accounts for the biggest portion of the total cash flow. So the duration is going to be a number very close to the time to maturity. For example, a 5-year coupon bond duration is going to be a number very close to 5. It's going to be 4 point something. While the duration of a 30-year coupon bond, the duration number will be very close to 30. Rule number 4, the duration of a coupon bond is higher when the bond yield to maturity is lower. So referring to bond C versus bond D, if the bond yield initially is higher, the sensitivity to the percentage change in the yield is smaller. This picture plots the 4 rules we just mentioned. On the vertical line we have the duration, on the horizontal line we have the maturity. So the rule number 1, zero coupon bond duration is the maturity. So you can see this is a 45-degree line. For example, a 20-year maturity zero coupon bond, the duration is 20 years. Rule number 2 says duration is smaller for bonds with larger coupons. If you look at the 2 pink lines, the dark pink line has a smaller coupon, 3%. The light pink line has a higher coupon, 15%. Both bonds have the same 15% yield to maturity. As you can see, the duration of the smaller coupon bond is higher than the 15% coupon bond. Rule number 3 says duration generally increases with its time to maturity, which is true for all bonds in this picture. The longer the maturity, the longer the duration, which is true for all 4 bonds. Rule number 4 says the duration of a coupon bond is higher when the bond yield to maturity is lower. So when we're comparing the gray curve and the light pink curve, both of them have 15% coupon rate. Well, the gray curve has the yield to maturity of 6%, which is lower than the yield to maturity of 15% for the light pink curve. You can see the lower yield to maturity bond has higher duration than the light pink curve. Now we have learned how to calculate the duration. We can use the duration to calculate the percentage change relative to the percentage change in the yield. So the percentage change in the price is delta P divided by P. Delta P is the dollar amount change in the price. Percentage of the price change equals minus duration times the change in the yield divided by 1 plus the yield. We define the modified duration d star equals Mercaldi's duration divided by 1 plus y. Then we can simplify the formula as percentage change in the price equals negative duration modified duration times the change in the yield. I will use the following example to show you how we use the modified duration to calculate the percentage change in bond price. We have an 8% semi-annual coupon bond, 2 years maturity. Yield is 10%. Use all the information, we can calculate the bond price, $964.54. Plug in all the numbers, we can calculate the duration, which is 1.8852 years. Well, actually using the formula, what the number we got is 3.7704 semi-annual periods. But we have to quote the duration in terms of years, so we divide that number by half. What happened to the price if the semi-annual interest rate goes from 5% to 5.01%? The yield to maturity is 10%, which is the annualized number. To calculate the semi-annual number, we cut it by half, 5%. We're going to use two methods to calculate percentage change in price. The first one is the direct method. We're going to actually calculate the price change directly. So first of all, we calculate the bond price using the old rate, 5%, before the change. So P0 is the original price. Plugging in 5% semi-annual interest rate in the formula, the bond price is $964.54. And then we're going to calculate the new price, P1, using the new interest rate, which is 5.01%. So all else are the same, but now we change from 5 to 5.01%. The new price, P1, is $964.1942. So the percentage change in the price will be P1 minus P0 divided by P0 times 100%. You can see the percentage change in the price is negative 0.0359%. Because we are seeing an increase in the yield, there is inverse relationship between the yield and the price. So an increase in the yield results in a decrease in the bond price. The second method, we are going to use the approximation using modified duration. So the modified duration d star equals the Mercaldi's duration divided by 1 plus y. And the percentage in the price will be negative modified duration times the change in the yield. We already calculated the duration, which is 3.7704 semi-annual periods. The modified duration will be Mercaldi's duration divided by 1 plus y. So here, Y is the original yield, semi-annual yield, 5%. So the modified duration is 3.591 semi-annual periods. Then we can directly calculate the percentage change in the price, which is negative modified duration times the change in the yield. The change in the yield is from 5% to 5.01%. So the change is 0.01%, which is calculated as 5.01% minus 5%. So the percentage change in the price according to this approximation using duration is negative 0.03591%. As you can see, the approximation using the duration is very close to the actual price change calculated in the first method. Now I want to show you another example. 2-year zero coupon bond and 10-year zero coupon bond with initial yield 8%. What is the percentage change in price of the bond when the yield increases from 8 to 10%? We are going to use two methods, the actual price change and the approximation of the price change using duration. So first of all, according to our rules, zero coupon bonds duration is the maturity. So the 2-year zero coupon bond Mercaldi's duration is 2, while the 10-year zero coupon bonds Mercaldi's duration is 10. In this, first, we are going to use the duration and modified duration to calculate approximation in the price change. For the 2-year zero, the Mercaldi's duration is 2 years. Modified duration is 2 years divided by 1 plus y. Y here is the original yield to maturity. The modified duration is 1.852 years. Then we can calculate the estimated percentage change in the price, which is minus change in the yield times modified duration, which is minus 2% because the yield increased from 8 to 10%. So it's going to be 2% change times modified duration 1.852. So the total percentage change in the price is negative 3.7%. Similarly, for the 10-year zero, duration is 10 years. Modified duration will be 10 divided by 1 plus 8%, 9.26 years. Estimated percentage change in the price, plugging all the numbers, is negative 18.55%. As predicted earlier, the price sensitivity is higher for the long-term maturity bond. As you can see, for the same 2% increase in the bond, the 2-year zero coupon bond price dropped by only 3.7%, while the 10-year zero coupon bond price dropped by 18.52%. Now in this table, I showed you the difference between the actual price change and estimated price change. So we look at the first panel first. When the yield increased from 8% to 10%, in our previous slides, we have calculated estimated percentage change in the price for the 2-year zero is minus 3.7%. For the 10-year zero is the minus 18.52%. But those are estimated numbers using the durations. What are the actual percentage change in the price? Then we will have to calculate the actual new price P1 and comparing that to the old price P0. So the actual price change for the 2-year zero is minus 3.6%. For the 10-year zero is minus 16.76%. Then we look at the case of yield falls. Originally, the yield is 8%. What if the yield falls down to 6%? Because there is inverse relationship, we know the price percentage-wise will increase in the bond. So again, we use the estimated numbers using duration. Using duration, the percentage change in the price will be positive 3.7%. For the 10 years, will be positive 18.52%. The actual change in the price, again, you have to calculate the P0 and P1 and then take the percentage. The actual percentage change for the 2-year zero is 3.81%. The actual percentage change in the price of the 10-year zero is 20.55%. Well, as you can see, our approximations are pretty good, but the actual percentage change in the price is always going to be higher than the estimated percentage change in the price. So we need to pay attention to the limits of duration. Duration is only an approximation of the percentage change in the price. And this is a linear relationship. Underestimate the increase in the bond price when the yield falls, and overestimate the decline in price when the yield rises. The limits of the duration is plotted in this picture. The blue line is the estimation of the price change in response to the yield change, which is a linear or a straight line, while the actual change in the price versus the change in the yield is a curve or is a convex function. So the difference between the pink curve and the blue curve is the estimation error. And in this picture, we showed you the percentage change in the price versus the change in the yield again. The light pink curve, the straight line, is the duration approximation, is a linear function, so this is a straight line, while the actual price change is a convex function, is a curved one, which means if you look at the 0 percentage change in the yield on the horizontal line, okay, when the change in the yield is very small, let's say between 1%, then the estimation using the duration is going to be very accurate, very close to the real change in the price. But the actual change in the yield is high, say 4% decrease or 4% increase, then you can see the estimated using the straight line duration method is going to significantly underestimate the percentage change in the price comparing to the curved dark pink line. In this, which statement is not true? A. Holding other things constant, duration of bond increase with time to maturity. Correct, because duration is always going to be a number close to the yield to the maturity, time to maturity. So the longer the maturity, the longer the duration. Given time to maturity, the duration of zero coupon bond decreases with yield to maturity. This is wrong because for zero coupon bonds, the duration is the maturity. It is independent of the yield to maturity. Statement 3. Given time to maturity and yield to maturity, the duration of the bond is higher when the coupon rate is lower, which is correct as we showed before. Duration is a better measure of price sensitivity to interest rate than its time to maturity, which is correct. That is the whole purpose we are calculating the duration. In this, par value bond XYZ has a modified duration of 6. Which one of the following is true? Well, the statement A is right. If the market yield increases by 1%, the bond price will decrease by $60. Let's see. We first calculate the percentage change in the price according to our formula. So the percentage change in the price is minus 1% times modified duration. Modified duration is 6 according to the question. 1% is the increase in the interest rate. So an increase of 1% in the yield will reduce the price 6%. So 6% decrease times $1,000 face value, which is $60. In this, which of the following bonds has the longest duration? Well, as I mentioned before, the duration is very close to the time to maturity. So we have 8-year and 10-year maturity bonds. The 10-year maturity bond will have a higher duration because their duration will be a number very close to 10. So we're comparing C and D. C has a 5% coupon. D has 0% coupon, means D is a zero coupon bond. For zero coupon bond, the duration is 10 years. While for coupon bonds, the duration is going to be a number smaller but close to 10 years. So our answer is D. Zero coupon bond has the highest duration, which is 10. A 9-year bond has a yield of 10%, duration of 7.194 years. If the market rate changed by 50 basis points, which is 0.5%, what is the percentage change in the bond price? 100 basis point is 1%, so 50 basis point is 0.5%. The percentage change in the bond price is, according to the duration method, we first calculate the modified duration, which is duration divided by 1 plus 10% yield, 6.56. Percentage change in the price will be minus modified duration times the change in the yield, which is 50 basis points. So the change in the price will be negative 3.27%, a 3.27% decline.